Okay, let's jump right into this explainer. We look at buildings and roads every single day. Construction materials are quite literally the foundation of our world. But what we don't usually see is the staggering amount of heat, energy, and, well, microscopic chemistry required to create them. Today, we're going to investigate the invisible, yet massive air quality challenges tied to these materials and see exactly how on-site fuel combustion emits pollutants you definitely need to know about. We've got a really interesting micro to macro journey plan for today. We'll start with the construction materials footprint, then define criteria air pollutants, dig into hazardous chemicals and organic compounds, look at heavy metals in production, and finally, wrap up with the very real health, environmental, and financial risks. All right, Section 1, the construction materials footprint. Let's get right to the source. To really understand this footprint, we look to the SASB standards, which the International Sustainability Standards Board actively encourages everyone to use. Think about making cement or glass for a second. You aren't just moving dirt around. You're firing up kilns that burn hotter than lava. It's this intense on-site fuel combustion and the raw production processes that pump out a highly complex mix of air pollutants and hazardous chemicals. And tracking this stuff is absolutely crucial. That brings us to our main cast of characters. The standard flags 7 specific emissions of concern. We're talking nitrogen oxides, sulfur dioxides, particulate matter, dioxins, volatile organic compounds, polycyclic aromatic hydrocarbons, and heavy metals. Basically, this list is the exact air quality dashboard that regulators and savvy investors are keeping a very close eye on. Moving to Section 2, defining criteria air pollutants. Let's translate some of this chemical alphabet soup. First up on the list is NOx, or oxides of nitrogen. Now, notice the precision required here. The standard explicitly includes NO and NO2, but it intentionally leaves out N2O or nitrous oxide. Why? Well, because in this context, precision is everything. We need to measure the exact nitrogen compounds escaping the fire to gauge their localized environmental impacts accurately. Right next to it, we have SOx, which covers sulfur dioxide and sulfur trioxide. These are your classic, harsh byproducts of burning fossil fuels at extreme temperatures. If you're familiar with acid rain or severe respiratory issues in industrial communities, well, these are the exact chemical compounds at fault. Then there's PM10. This is airborne particulate matter. Think microscopic dust, soot, and liquid droplets. To give you a sense of scale, a single human hair is roughly 70 micrometers thick. PM10 is 10 micrometers or less, so we are talking about jagged, tiny particles generated from crushing stone or burning fuel that are literally small enough to bypass your body's natural defenses and get lodged deep inside your lungs. Section 3, hazardous chemicals and organic compounds. This is where the manufacturing process gets incredibly complex. You might actually spot the acronym PAHs buried deep in a corporate sustainability report and think, okay, what exactly are we measuring here? Unlocking this jargon is super important if we want to really grasp industrial air quality. So PAHs stands for polycyclic aromatic hydrocarbons. These form when organic material doesn't burn completely. Imagine the toxic blackened char on a badly burnt piece of food, but scaled up to a massive industrial level. They are organic compounds with 2 or more fused benzene rings. And tracking them basically tells us how efficiently or inefficiently a kiln is actually running. We also track VOCs, specifically non-methane volatile organic compounds. These are carbon-based chemicals that have a really nasty habit of triggering atmospheric photochemical reactions. What does that mean in plain English? Well, when these compounds hit sunlight, they create smog. So this is exactly where corporate emissions data meets the visible air quality of local neighborhoods. Next up, dioxins and furans. The standard is incredibly strict on this one, requiring entities to track 17 specific toxic congeners that contain chlorine. And there's a really good reason for that strictness. These are quite literally some of the most highly toxic chemicals known to science. Even microscopic trace amounts will immediately trigger massive regulatory scrutiny worldwide. All right, Section 4, heavy metals in production. Let's see what happens to the raw materials themselves. Because beyond the gases, the extreme heat used in production actually vaporizes elements right out of the raw earth. The SASB standard specifically demands that facilities track 3 highly toxic heavy metals released during production: lead, mercury, and cadmium. Pumping vaporized mercury, for example, into the air is a profound environmental hazard. That makes tracking these specific heavy metals an absolutely non-negotiable metric for any responsible operator. So how do we make sense of all this different data? It's simple. Metric tons. Every single one of these 7 air pollutants, from the nitrogen oxides down to the very last drop of mercury, has to be measured and reported in metric tons, released into the atmosphere. This gives us an apples-to-apples baseline. It lets an investor instantly compare a cement plant in Europe with an aggregate producer in North America. Finally, Section 5. Let's zoom out and look at the real-world health, environmental, and financial risks. There's a quote from the SASB Air Quality Topic Summary that really hits the nail on the head. It basically points out that unmanaged emissions are a direct threat to financial stability. If a facility is just blindly pumping out PM10 or heavy metals, they aren't just damaging the local environment. They're staring down the barrel of higher capital expenditures and devastating legal penalties. And this is where quantitative accounting standards come in. By tracking metrics like SASB metric EMCM 128.1, entities can pinpoint exactly where localized human health impacts translate into severe exposure to legal and regulatory risks. This acts as a literal bridge between chemistry and finance. It turns an invisible plume of smoke into a hard, measurable number right there on a balance sheet. When you look at the outcomes side by side, the business case is crystal clear. Unmanaged emissions mean fines, lawsuits, and really expensive rushed fixes. But active management, think about it. A plant that fine-tunes its process to burn fuel more efficiently produces fewer toxic PAHs, for sure, but it also spends significantly less money on fuel overall. It's operational efficiency driving environmental protection. A total win-win over time. Which leaves it with a critical question to think about. Are the construction material entities you might be investing in actively managing their microscopic risks to protect their macroeconomic future? The standards are absolutely clear, and the data is out there. The next time you walk past a towering concrete skyscraper, just take a second to remember the invisible metric tons of data behind it. Thanks for joining me on this explainer today. I'll catch you next time.